días. Good morning, everybody. Can you hear me? So, for me, it's a pleasure to introduce you to Binbin Zhang. Binbin has been here for 3 years as a Quadrilateral Fellowship, and he's leading soon because he's taking a permanent position in Nanjing University in China, where I'm from. I met Binbin a long time ago because he did his PhD degree with Bin Zhang, whom I know for many years, and then we have met in several conferences. So he got, as I said, his PhD in 2011 at the University of Nevada, Las Vegas in the US with Bin Zhang, not to confuse with Binbin Zhang. And then he got a first postdoc at Penn State University, working in Swift with David Barrows. Then in 2013, he moved to the University of Alabama in Huntsville to work with Valerie Conotto in the Fermi team. Then he came here to Granada and stayed his head. He has been very much involved in VRBs, especially in prompt mission, also starting after mission. Recently, he became involved in the follow-up of the gravitational wave alert regarding this trigger on 17 August, which you are already familiar with because you have attended a talk by Alex and Luca on the past weeks. And now Binbin will tell you about what he has been working in this event and the paper that he has submitted to Nature Astronomy a few days ago. You may also tell them the history, why they did not want you to submit earlier as we intended to. And well, that's all. I'm looking forward to hear you. Thank you.
Thank you, everyone. So this is the talk about GRB 1708-17A, this particular GW event. So I'm from the RAE group in this institute. So this work is in collaboration with a lot of colleagues from US, Spain, of course here, and Italy and China. So our observation involve a lot of observation taken from RAA, and this is a press conference in October last month, where Alberto presents our results in this conference. So first I'd like to talk about some background of the GW and gamma ray burst. So the background is like this. So because GRBs, short GRB are related to the related to the binary neutron stars. So we need to first find the evidence for the binary neutron stars. And then we should talk about the link between the short GRB and the binary neutron stars. And then we should talk further about the short GRB and gravitational waves. So first of all, the evidence of the binary neutron stars. And this is actually a very old topic. So if you can look at the literaries, and this actually began with Hughes and Taylor in 1975, who got the Nobel Prize in 1993. So this is first measurement of a pulsar. Is actually a binary system. When you look at the parameters, and then you can calculate the M1, M2, you actually got the mass, and got the period, and got the P dot. And then it turns out that they have to be the neutron star. And this is actually the first measurement. And from this, they can calculate from the relativity, you can actually predict the period of decay. And this is very consistent with the gravitational wave prediction. And then the LIGO actually was motivated by this event, and later on they become a real action. And further, we actually have more binary neutron star systems in our galaxy, and this is like a lot of candidates here. You can check the mass. Actually, the mass has a larger range. For example, they have like a 2.6 solar mass and 2.5 solar mass. which was not supposed to be like this, because we think this is over the Chandrasekhar limit, right? But you can see that a lot of binary neutron stars have a very large range. So that's why for this particular event, we cannot constrain whether it is a black hole or neutron star. And so we do see the binary neutron star exist in our system, in the galaxy and in the universe. So that's why we say that it's possible to have a GRB from a binary neutron star. So why there is a short GRB from the binary neutron star? And because a short GRB can be produced during the merger of a binary neutron star system. So why do we say this? Because this is also an old topic. If you look at the papers back to 1984, and several authors already proposed that a potential GRB progenitor can be a merger of a neutron star binary. And they later on, Paczynski and Goodman, and in 1980s also proposed the same idea. And this topic was very detailed discussed in this paper, Nature 1989. And actually, if you look at the paper, it is cutting very details how this short GRB can be produced during two neutron stars was merging together to a black hole. And so the picture is like this. So later on, this topic was further discussed in 1991 and 1992 and 1993. And during these works, two scenarios was proposed. And first one was black hole plus accretion disk. And the second one is millisecond magnetas plus a disk. So the central engine actually can be two possibilities. First, let's look at the black hole plus a disk. So in either way, when the two neutron star mergers or two compact thing mergers, they can form a black hole plus a disk. And this and the energy from this system can be 0.03 to 0.3 solar mass, and forming the disk mass will be 0.1 to 0.3 solar mass, and which depends on the mass ratio. And also, if you look at the time scale, and this is very important because this can be related to the time scale of the short GRBs. And if we put these numbers in, and if we calculate the accretion rate and the time scale, it turns out to be 0.2 seconds. And that's why this scenario was thought to be related to short GRB, and because this time scale very like a short GRB time scale. And then how a GRB was produced. Because we form a disk and black hole, this is not the whole story. You need a jet to be launched. And then when the jet accelerated the electrons, then electrons can emit a single-jon radiation and produce a gamma rays. So the important thing is to launch the jet. So how to launch a jet in this system? The first scenario was neutron star-driven jet and neutrinos-driven jet. And then if you think of this neutrino-driven jet, you can estimate the energy is 10 to 49, which is very consistent with the observation of short GRBs. And the other scenario was the BZ jet. This BZ jet goes to a larger energy, it's 10 to 51, but still consistent with the short GRBs if you consider the viewing angle or beaming angle effect. So either way, so using this black hole plus a disk scenario, you can still produce a jet which produces a short GRB. So as we mentioned before, there's another scenario which is millisecond magnetas. So if it is a magnetas, we can still have several different kinds of magnetas. One is a supermassive neutron star or a quark star. So some authors propose it can be a strange quark star. Or this supermassive or hypermassive are non-stable. So eventually will collapse to a black hole. But during this collapse between the neutron star and black hole, there can be some observational features. And then if it is a stable neutron star or quark star, we don't have this in-between features. And then the energy comes from the rotation energy, or the accretion disk of the rotation. So, so either way, we can, when we compare the observation evidence and these two scenarios, we do have some observational evidence to say the short GRB are related to the neutron star or neutron star black hole mergers. And for example, we do have the energy, like the typical energy of short GRB is 10 to 48 to 10 to 51 ergs, and rotation, the duration about 1 second. This is very consistent with the time scale, right? And also the media density is very low, and this is very consistent with the merger environment. And for example, when the neutron star happens, it's mostly not likely to happen in the star formation region. So its density should be low, and we do observe this. And we also have the host galaxy types are very consistent with the short GRB scenario, and we don't have supernovae observed for short GRBs, so this were considered too. But this are also all of these are speculations. We don't have direct evidence to say the short GRB are directly related to the neutron star merger. So we do need a gravitational wave detection to test this model. And on the other hand, we do have numerical evidence. So a lot of groups perform the numerical simulations, and they do put for example, a black hole and a neutron star, and let them evolve and observe the merger process, and they do observe if disk was formed. And if they put two different mass of the neutron stars, they also observe the neutron black hole was formed and the disk too. And so this is different mass of the black hole and neutron stars. And they do observe an additional outcome, which is the ejecta of about 10 to the minus 4 and 10 to the minus 2 solar mass, and with a velocity of 0.1, 0.3 speed of light. And this kind of part is regarded to be a kilonova complement, which is get out of the disk in the other direction, which can form a kilonova. So this is a summary for the post-merger outcome. So we can either form a fast-spin black hole, or hypermassive millisecond magneta, or supermassive magneta, or stable magneta. And in either way, we should form a disk, accretion disk, whether it's powered by neutrino dominated or the Biset effect. And we should also get an ejecta with relatively low mass and velocity of 0.3, 0.2, or 0.3 speed of light, and this complement is kilonova, right? So this is the summary, but the gravitational wave signals are a key to identify these products and to test the hypothesis of the GRB and binary neutron star acceleration. So this is another picture showing this, showing the black hole scenario. So for black holes, we have a short GRB and afghans, and we have a kilonova, and we also have the afghans emissions. And if we compare the black hole with the magneta, you can see the difference here. The difference is mainly depends on the energies of the merger product. If it is magneta, the kilonova complement is much stronger, and it causes luminous optical transit, and it can power by several days. And if it is a black hole, and this complement is relatively weak, it can be optically dark. So this is very important for this particular event of GRB 08 to 78. We didn't observe a very strong optical transit, so it's most likely it's a black hole, not a magneta product. so this is the scenario for the binary neutron star merger. And then we can talk about the links between short GRBs or the binary neutron stars and the gravitational wave. So this is because the gravitational wave was produced during the binary neutron star and neutron star black hole merging. So why we say this? Because theoretically speaking, the binary neutron star or neutron star black hole merge event is the efficient GW radiator, and this waveform, GW waveform, is well known, and we will calculate a typical neutron star merge or neutron star black hole merge. The energy, the gravitational energy, is about 0.03 solar mass times c squared. And then you can, depends on the merging process, the gravitational signal can happen anywhere between -5 or 1 seconds within the GRB trigger. And of course, you still have different scenarios. So this, you can see that the neutron star merger eventually can produce a stable neutron star, or a black hole, or a supermassive black hole with accretion, or no accretion black hole. And then, depends on the mass, you can still have several options here. So the GW signal is actually very important to identify those kind of process. You can, by checking the GW event, the signal, you can, in principle, constrain the mass of the two merger star, and then you can also even check the merger products. And this is because for gravitational signal, you have the frequency here, and also the f dot is a derivative of the frequency, and then you can calculate the Chirper mass, and also the tidal love parameter, which measures the geometries of the merger product, and also you can measure the tidal deformability, which is lambda. You can also measure lambda wave, and these two parameters can tell you the geometries of the merger product. Also tell you the radius. You can see the radius. There's a parameter of radius, and based on the radius and the mass, you can basically calculate whether it is a black hole or in a magnetar. So this is very important to study the final products of the gravitational event. However, this event, GW 7008 to 78, the signal is too weak, and unfortunately we didn't be able to constrain the final products in this event. Here is let me see the movies whether it works. So this is two neutron star, and you can see basically the gravitational wave destroy the space-time, and during the merge, and they form a black hole, and then they form a jet, and they form a kilonova around the jet and the afterglow here. And you can see the gravitational wave was formed in the beginning and will become very strong during the merger, become a black hole. So this is the whole background. And so before we observe the GWs 7008 to 78, so the first question is, what did we expect to observe as the first GRB-GW oscillation? So this is an important question before the LIGO really takes the observations. Of course, we know that GRB are most promising candidates for LIGO GWEM counterpart. But the first question is, what can we tell from the joint detection? And before LIGO, before the LIGO launch 01, which is 2015, and we first wonder what happens if there's no detection. So this is an important question. So actually in 2015, we've noticed the date is March 15, right? And the first detection of JW event is 2015 September 15, right? This is half a year before the first detection. So during this meeting, the Fermi team and SWIFT team and LIGO team discussed together what happens if we observe zero event. If we look at this clearly, there's 0. And what happens if we observe 1 event? What happens if we observe 10 event? And what happens if we observe 100 event within 10 years, right? So the zero event is important because if we really didn't observe nothing during the first 10 years, so because the LIGO sensitivities can be reached within 10 years, it's very sensitive in 10 years later. We're supposed to observe under this 1. But if we do observe 0, then we can say something about the GRB progenitors. It cannot be neutron star merger because neutron star merger should produce a very strong gravitational wave. And if it is within our detector horizon, and if we cannot observe anything, then the progenitor can be a problem. Or the beaming angle will be very different. Most of the GRB are pointing to the other direction. This is not very likely, right? Or the GRB most likely happens in very far away beyond the horizon. So there are a lot of possibilities. But in any case, if we did observe 0 event, they can give a lot of constraints on the GRB models. And of course, the other thing is Einstein was wrong, and most people, so we do think this is not likely. So because we do see the pulsar, we see the pulsar event, and it's very evident to test the general relativity, right? And so what do we tell if we observe 1 event? And this is actually the case for our GRB 1708 to 78, right? So if we observe 1 event, we can tell the progenitors. And for this event, we do get some conclusions of the progenitor, and we can tell the timing. Timing means when did the gravitational wave happens and when did the GRB happens. And also we can tell a bit something about the kilonova, whether there is a kilonova or not. And in 10 years later, or 5 years later, we may have a sample of 10 events or more. Then from a large sample study, we can tell more about the progenitor accretion outflow properties. We can study more beaming, which means what's the distribution of the angular, the angle of the jet, and also the population of short GRBs, and also the equation of state, and also we can use this sample to study the cosmologies. This is the implication from different samples. But the problem is that the detection rate, so why we discuss the 0? Because the detection rate was thought very low. So how low is that? So this is a paper in 2015 by LIGO team. So they have 2 different scenarios. One is a binary neutron star merger, and the other one is a neutron star black hole merger, right? So in each case, we will look at the GWGBM detection for Fermi, or for SWIFT, or Sky. You can see that in 2017, each year you can detect the 0.03 event or 0.9 event. This is not very likely to happen in this year, right? We are in 2017. So the hope was put on 2019, which is the year after next year. And in that year, we can in principle observe 0.1 or 2 event each year. The rate is very low. And for the neutron star black hole mergers, we have a similar rate. So the hope was put on 2019. And a more careful study was performed in 2016 by Glenda Group. And they used the LIGO horizon, which is 200 MPC, this advanced LIGO horizon. And they, by assuming a a opening angle 3 to 6 degree, and using a lot of statistical relations of short GRBs, and they estimate the rate to be 0.7 each year within the LIGO horizon. And also, if you're using more plausible models, you can get 0.03. And still, this is too low. And so 0.03 a year, that means 30 years you can observe one event. And you can transfer to a rate, the other form of rate, which is a few cube GBC per year. So this is a very low rate. So from Granada's paper, it was thought at least 30 years needed for LIGO to observe one GW and short GW event. So the hope, so this is not very likely to happen according to this estimation, right? So the hope was given to short GW orphan afterglow. So why is orphan afterglow? Because orphan afterglow was not depends on the angular, depends on the angle. So you don't need for the GRB to point it towards us. So we can observe the orphan afterglow after the GRBs. Maybe we can observe a afterglow and gravitational acceleration. And so next question is, if we do observe a short GRB, and if we forgot that event, what kind of short GRB did we expect? And so we just use very simple numbers. And advanced LIGO horizon to 200 MPC. And short GRB energy, we just see the energy in my last slides, is about typical energy. We put a 10 to 50 ergs, right? And duration 2 seconds. And we assume an on-axis. Then we calculate the flux. And it turns out the flux is 10 to minus 4 ergs per centimeter square per second. And this flux is very large compared with the other GRBs, or even the brightest short GRB. The brightest GRB is called the nearby monster. It's called 130427A. This is very, very bright. It's almost the brightest GRB in history. It's about 7 times 10 to minus 4. And if we do observe something nearby within the LIGO horizon, it's going to be very bright, even comparable with this brightest GRBs. So what do we expect? We should expect very bright short GRB as the first LIGO detection. So what do we really observe? So the story changer is GRB 170870A. So this GRB happens in this date and this time. This is GRB time. You look at the GRB time is at 0.6 seconds, 0.47. And then the GW event happens about 2 seconds before the GRB event. It's actually 1.7 seconds earlier before the GRB time. So this is the first GW and electromagnetic event in history. We currently have more than 100 papers today. So a little bit more about the time. So we do have this time. This is like a physical time. This real GRB time happens at this time, and this real gravitational wave time. And this time means the two neutron stars merge to a black hole, or something similar to black hole. For example, a magnetar, right? And this is physical time. And Fermi notice time is only 14 seconds after the GRB time. And LIGO pipeline time, you look at this time, it's about 6 minutes after the gravitational wave event. This is internal time. We don't know this before this date. Because before this time, the outside world, like MOU people know this, is about 20 minutes later after this time. So the question is whether the GRB signal help the LIGO to find or confirm the GRB event. The answer is no. So because the LIGO using a latency search event, they search the archive data after the signal. So they need like 6 minutes to confirm the signal. So they actually use the binary merger search for this particular event, and this merger event they use about 6 minutes to confirm the event. So how special is GRB 700870A? So I'll talk about this in 3 aspects. First of all, the gamma ray only, and then we will take care of the distance, and then we will put together the multi-wavelength or multi-messenger informations. So for GRB only, what we can say is that this GRB is slightly weak, but still normal GRB. And this is the light curve of this gamma ray burst 700870A. This is the whole energy light curve. You can see a peak at 0 seconds, and then another small tail peak and here. And then if you put this in different energy bands, you can see the evolution of the pulse shape. But you do see several different features for these 2 peaks. So it has a significant main peak, but it's not bright. So when I say bright, it's not bright like this. This is another typical short GRBs. It only lasts like 1 second. But when you compare this one with this one, this trigger is much weaker than this bright short GRBs. And so this one is much brighter than the background, but still significant. So it triggers the Fermi event. And if we compare this one with other short GRBs observed by Fermi, we do see a lot of similar ones. So if we randomly choose a lot of short GRBs in the Fermi sample, we do see a lot of similarities between those short GRBs. And actually, if I take out the name, you cannot tell which is this GW event. So actually, this is the 7008 to 70A, but others are other short and weak GRBs. So there seems like a weak tail and 1 second. So this is so we use a particular 2D technique to identify this tail. This is a little bit similar with the optical techniques. This is burst plus background, and this is time. So we see the different energies in different time. And then we get a background here, and then we use the total minus the background, we get the burst contour it's called the count map of the energy versus time diagram. We can see that within the 5 sigma, we can identify 2 regions. The first region is the first peak, and then the second peak has a second region. And from this one, you can also see the spectral difference. You can see that for the first peak, we have more lower energy photons, and here we have less lower energy photons. And actually, this can tell that the spectrum are actually very different. But for the spectrum, so the main peak, this is very typical spectrum. For GRBs, we have a band function spectrum. For this one, it also can be fitted by a similar function. We fitted this with the cutoff polo. The E peak is about 158 keV. The low energy spectral index is about 0.66, and this is very typical compared with other short GRBs or the whole GRB sample. Not only we're doing the cutoff polo, we also try the physical models. So we also use a photosphere model, which is most likely the thermal origins. We also use a synchrotron modeling here. And so this is really physical models, and we look at the parameters. They have like a 8 parameter or 7 parameters, including the initial lens factor and the photosphere radius and the theta angle, which we assume a structure jet. And so we actually calculated the photosphere spectrum from the initial photosphere radius, and it turns out this spectrum, cutoff polo spectrum, is It's still consistent with the photosphere model, but it's also consistent with synchrotron model. And this may be because the model has a lot of flexibilities. We cannot constrain very well, but in our paper we think this is more favorable, mainly due to the delay time of the 1.7 seconds. So this is the moon peak, and for the second week peak, we try to figure the spectrum, and it turns out it's consistent with the black body, and the temperature is about 10.8 keV. It's consistent with the black body. However, the non-thermal origin was not ruled out, and this is because the photon numbers are too small. So even there are two parameters, we cannot rule out the synchrotron origin or the non-thermal spectrum. However, the lower energy index are very hard, so there may be some evidence showing that it's more likely a thermal complement. So this is a summary about the from the emission without considering the distance. So the duration about 2.2 seconds. The spectral peak energy is about 150 keV. The fluence is typical, about 10 to the minus 7 ergs centimeter square, and spectral lag is considered with 0. And this is very consistent with the short GRBs. So if we pose this particular GRB with the whole sample of short GRBs, you can see that this short GRBs, in terms of the signal to noise, is typical. In terms of the fluence, is typical. In terms of the peak energy, is typical. And we'll pose this into the hardness ratio versus 290, and this means the spectral hardness ratio. This person is in the region out here is still typical. And we compare the fluence versus peak energy, and this GRB goes to here, and it's still it's in the lower part. It's in the lower part of, but still typical. And we also compare this GRB with other GRB for the F parameter. F means it's like an iceberg effect. It means a little tip, whether it is a little tip of a long, intrinsically long GRBs. And this GRB doesn't show any features among the whole sample, so it's still typical. So all I can say is the normal short GRBs, according to the prominent image properties. However, if we put the distance there, we'll get several different conclusions. So we know the distance because we know we can measure the host galaxy, and we know the distance is 39.4 mpc, and the redshift is about 0.09. And then we can calculate the energy. The energy is about 4 times 10 to 48, or 46. And this is very low. So in GRBs, we have the Amati relation, which is ESO versus E peak. And we put this GRB in this diagram. You can see this GRB is at this particular position. So it's the lowest short GRBs in terms of the isotropic energy. And this is long GRBs. And there's only one long GRB has a lower isotropic energy than this one. So in terms of the energy is the lowest short GRBs. Luminosity is very low, also very low. It's 10 to 47. So the question is how to explain the extremely low luminosity and low energies. So one scenario is that you think you can calculate the off-x. So if you think of off-x, the first impression is that you just assume a uniform jet, and then observer is at this angle. Then you only observe part of the jet, and then you can basically calculate the energies. The energy will be a gamma minus 4 power. then you can decrease the energies by gamma's minus fourth power. So if gamma is 100, then you can decrease the energy by a factor of 8 degrees, right? Then you can solve this problem. But the problem is the T90. So if you assume these features, the T90 can be increased by gamma squared. And if gamma is 100, then the intrinsic duration is 1 second, then the duration will be 10 to 4 seconds. And this is much larger than the observed duration, which is 2 seconds. So you cannot assume a uniform jet. So the only thing you can assume, if you think this is off-X, only thing you can think that it has to be a structured jet veiled with off-X. So in terms of structured jet, the most natural scenario is that there is a jet concours geometries. And so jet concours is like this. So when the jet propagates outside, there's some concours emissions and around the jet, and you actually observe such emissions. And these particular features are consistent with the 28-degree measurement from the GW data. So this is the concours numerical simulations. So basically you observe some emission from this part. And you do have a jet along this one, but you have the emission from here. But the other thing, if you don't think that it is off-X, then you can also think that it is intrinsically low luminosity for these GRBs. That means you have to assume not all neutron-star merger produce a short GRB. This is also can be understandable because we should have a distribution of the accretion rate. And for some accretion disk, when some accretion disk with lower accretion rate, and some may produce a weak jet, and some may produce even weak, some field jet, and which not produce a short GRB. There should be a distribution. Or the magnetic field is weaker, so it's not going to produce a bright jet. And that also produces low luminosity GRBs, or some GRB like this one. So that means you will assume this is true, and you can basically, based on this event, you can recalculate the rate. So let's do some simple math based on this one. So GBM we observed 9 years from 2008, right? And then we observe one GRBs like this, which is definitely from the gravitational wave event, and definitely from the neutron-star merger. And then this should be a lower limit of greater or equals to than 1. So in 9 years, we observed one event like this, and then we assume a duty cycle of 0.5, which means the Fermi GBM was observed full sky half of its time. So then 9 years times 0.5 is 2.5 years. And we assume a 4 pi field of view, and we assume the volume to be 4 pi d cubed divided by 3. And the dl is the maximal distance. And we didn't put 40 here, which is the distance of this event. We put a 65 MPC. And this is because we can put this burst to further distance. For example, we put a 45 MPC, we can still see this event. We put a 55 MPC, we can still see this event. And we put to 65 MPC, and this one is consistent with the background. Then we think if we put this event to 65 MPC, we can still observe this event. Then we put these numbers in, and then we can calculate the rho, which is the event rate. And it turns out the rho is around 200 per cube GPC per year. And if you remember the Galanda result, which is the field cube GPC per year, that is a factor of 100, right? So it's much, much larger event rate, which means we should observe it's not 0.07 event a year. We should observe 100 times more event like this. So this is a very important implication by this event. And so on the other hand, we can estimate the neutron star rate itself by LIGO. So LIGO during the LIGO observational cycle, they observe one event. So that LIGO have the O1 and the O2. So O1 is about 1 year, O2 about 1.5 year. And then we put these numbers in. And because LIGO O1 and O2 have different horizons, and we put these numbers in. And similarly, we get the rate for neutron star merger event is about 1,100. So even if you compare these two, because 190 and 1,100, right? So although the error bars are large, within the error bars they're mostly consistent, but the central value are still different. And this can be understood by our previous conclusion that some GRBs are intrinsically low, and there may be some neutron star merger weak short GRB hidden in the GBM archives. So we already observed such short GRBs in our sample, but because we didn't have the GW trigger, we didn't know it is the neutron star merger, but it is there. So one of our projects is to search back the data in last 9 years and try to identify these sources. So from this, with considering the distance, we know that this event gave a promising rate for future GW and short GRB joint detections, and we should alert for these weak short GRBs. So we are currently developing a burst of interest alert system. So this system using the Fermi GBM information, and within 5 minutes we can determine if the short GRB is of interest of the gravitational or kilonova event. So within 5 minutes we can release the duration, the peak energy, the fluence, and the base distance. And this means most likely the distance is, if it is very interesting for GW event, the distance will be like for example 40 MPC or 60 MPC, and also base location based on the most likely gamma ray information and spectral shape. And this kind of information was not released by the GCN circular or GCN notice. So we have a particular system to process this using the prompt gamma ray information. So we can further release the observational strategy, and we can tell the ground telescope when and where to point at. And this is some example for this particular 7008 to 70A. So we actually, for this GRB, within 5 minutes, we can calculate the spectrum. And the spectrum is very low resolution because the first data are very low resolution. So, but we still get the best result, and within the 5 minutes. So we got the location, we get the estimate duration. It's about 1.6 seconds, which is very consistent with the final result, and also fluence and flux. And we also get the light curve spectrum, and we also get the possible possible locations of the nearby galaxies. So however, this is maybe not an easy task because the error circles of Fermi GBM is very large. So for this red dots are the nearby galaxies. And for example, if you have one particular short GRBs, you can, within several tens of MPC, you can have a lot of nearby galaxies within its error circle. So you have to search a lot. And on the other hand, you have to have a tablet before this observation. So you have to compare whether it is a transit or not. So maybe not easy to identify, but we think it's a good start to try this. So next topic is in the context of multi-wavelengths or multi-messenger. So this GRBs actually have a lot of observations in optical and X-rays. And for optical, and we currently have 25 good data points, which is studied in detail by this paper. And so a lot of people doing the modeling, and the best model is actually a kilonova. And of course, the kilonova have different pictures, and several papers proposing a 2-component kilonova, and several papers proposing a 3-component kilonova, and plus a off-flex jet. The off-flex jet explains the non-detection of the X-ray afterglow, and it turns out off-flex jet is very consistent with the X-ray data, and the optical data is very consistent with the kilonova observations. And because we don't have a bright afterglow, and we don't have a very bright kilonova, and in our paper, we think a black hole product is very preferred for this particular event. And our Bootis 5 observations are important to the observation to this event too. So and for the one day, we observe a counterpart for this particular event, and the magnitude is about 18.2. So we include this in our paper too. And we also have neutrinos and very high energy observations, but all the data are up limit. So these up limits are consistent with the afterglow model, which is off-X afterglow. A few words about the delay time. So the delay time is 1.7 seconds. And if you remember, the duration of the GRB is about 2 seconds, right? And such a delay time, if you calculate the delay time, basically you can calculate the radius, right? Delay time, the radius is the gamma square delta t and c. So then it's automatically go to 10 to 14 centimeter. That centimeter is not likely to be the photosphere. So it directly offers a check of the emission site. So it also tells you the emission dissipation process, and also tests the photosphere model. And unless the gamma, the length factor is very small, then you can get a consistent radius for the photosphere. But you remember the spectral fitting, we're using a photosphere for spectral model, and that photosphere model actually uses a very small gamma there. So the gamma, unless you use a very small gamma, then you get a consistent photosphere model. However, you still need to explain the delay time. It's 1.7 seconds. So in our paper, we think that this scenario is more likely. So we suppose the emission model that invokes the synchrotron radiation in an optically thin region. This event also tells us a lot of lessons, including the equation of state, the mass injections, and the merger cosmologies, and neutrino physics, and dark energies, and the environment of the merger stars, and also host galaxies and polarizations. So there's a lot of topics in this event. So in summary, this particular GW and GRB event opens a new era in astronomy. And to me, I think this changed our understanding of short GRB rate. But we need more samples to confirm this, and I think future observation will tell us more. And we do confirm the neutron star merger of the short GRBs, and this is also important. And we do confirm the kilonova association of short GRBs. And we do have a lot of lessons on different topics of astronomy and cosmologies. And that's my talk. Thank you very much. So I'm moving to a new group in Nanjing University. So I'm going to form a new group. So we have a lot of fundings for visitors. So if you are interested, you're welcome to join. Thank you.
Thank you so much.
I'm sure there will be a few questions, because as you really said, this is opening a new era in astrophysics. I'm sure we will get some more alerts in the second half of next year when the new detectors will be operating again. Who wants to start chatting? Alex?
I hope I don't sound unfair, but I couldn't quite get out of your talk what exactly is the focus of your own paper, and why has it been submitted to Nature Astronomy and not just, say, AppJ or so? And Alberto mentioned in the beginning that you maybe should also say something about why the paper is only submitted now. I mean, you put it out with the first wave, right, on AstroPH back on the 16th of October.
We actually submitted the paper on September 12th in Nature. And because authors are some authors are not MOU, so the editor suggests us wait until the press conference and submit this to the Nature Astronomy. But you know, there are a lot of studies on this topic, and several papers have the overlap topics. But we are independent. We are also doing the independent study, and our paper. And if we compare our paper with other papers, our paper is the main paper, is the only one that doing prompt emission and implication of the rate, and implication of the merger products, and implication of the kilonovas. And I think we do a very comprehensive study and very from a different angle. And although we get a similar conclusions as a Fermi GBM team, but our paper I think are more physical and more interesting. So it's unfair we didn't get to Nature because we don't belong to the particular group. However, we think we still put our paper as early as possible. So answer your question, it's a comprehensive study.
Any other questions?
I'm puzzled a little bit. What is the? I mean, I saw that you had the borders observation. What is the campaign of borders? Is this just the one detection that you're putting there, and what is the contribution of the borders campaign into the paper?
Yeah. So this one gave us a data points that happens at the only day, right? The only particular time, there's only one data points.
Right. I'm going to explain later. This is data we're taking the second night. The first night, we imaged the nearby galaxies on the preliminary occasion, but we were unlucky because the real galaxy was out of the list of galaxies we imaged. So we only could get this image on the day 2 under very poor conditions, just a few degrees above horizon, as Juan Carlos knows quite well. And then the following week, the days it was quite weak. So we only had this data point, and it's part of the paper. It could have been part of another paper, but we decided to place it on the paper which was led by somebody of our group and not by some other collaboration.
Borders 3 was bad weather, or what? Because it was perfectly located for immediate follow-up. after the announcement. I mean, it was the first observatory that could have been going after it after the detection was announced.
I reply, if you don't mind. The mount was in Germany under repair at that time, so bad luck. Any other question? So then, if not, the last one for me. So then you expect that we will detect many more events in the next years, as you said?
It really depends on whether this one is so particular or just a normal one. So I think the second one or the third one will tell. So maybe next one will be very, very bright. Goodness. I think LIGO already gave a lot of surprise. The first surprise is the double black hole models, right? So it's unexpected. And then we think we detect the first Fermi event on the first one. It's very weak, but it turns out it's a controversial one. So there's this one. And then suddenly we detect this one. But this one is so weak. We didn't expect it so weak. So we don't know. So, but I think the rate should be much larger in principle. However, the second one, third one will tell whether it is really like off-X, it's so normal, or just this one, we are just lucky.
Okay, if not, then we will conclude here. Thank you, everybody, for joining us.